Hello, everybody. Thanks for coming to this session, and I wish everyone enjoyed the lunch. I personally did. Awesome food. So it's time to learn something. And today I would like to share with you our experience of integrating Spark MLlib and Apache Solr to have or to build a real-time entity type recognition, which we use to improve our query understanding, which ultimately benefit the relevancy of the search results that your search engine can return or retrieve to the end users. This is a teamwork from the search data science team at Career Builder. Khalifeh was our PhD intern who actually did all the implementations of the awesome things we're going to present today. And Mohammed, Trey, they are both in the search data science. A little bit about myself. I lead the search data science team. I have a PhD degree in computer science from University of Georgia. And I also organize a Southern Data Science Conference, which is the very first data science conference in the Southern states. It's going to be held this year, April. So why? Last year, I came to Spark Summit. I spoke about how to automate the evaluation of the search engine quality by using Spark. And this year, I'm talking about how to better understand the queries for better search experience. So why we focus so much on search at Career Builder? Because search is one of our core components in almost all of our products. You can think of it as the backbone for all of our products. That's why we care a lot about search. Search relevancy is kind of our #1 priority. And if you look to those numbers, so that just to give you some hints about the scale that we are talking about when we talk about the search engine for Career Builder, we receive more than 100 million searches per day. We have more than 1.5 billion indexed documents searchable. We run our own data centers with more than 500 search servers where we deployed Apache Solr. And we are now on our way to move to the cloud. So the agenda of this talk, I'm going to start by presenting the problem that we are trying to solve and why it is a challenging problem. Then I'll move and describe the system that we built to solve that problem. And then we'll share with you the experiments and results. So what is entity type recognition? In some literatures, you will find people refer to this problem as NER, named entity recognition. Others refer to it as entity type recognition. Anyway, this problem or this process, you can think of it as two-steps process. In the first step, we try to identify the tokens or regions in the text that actually represent or refer to entities. These entities could be a person, could be a location, could be a company, organization. So you need to recognize within this text which regions or which tokens actually refer or represent those entities. The next step, once you recognize those regions or those tokens that represent entities, the next step is to classify or categorize those entities into their appropriate types. So if I got Michael from the text, I need to say now Michael is a person. If I got Databricks, I should say Databricks is company. This is the problem. Cool. So in the example on the screen, this problem usually if you go to the literature reviews, if you go to the online resources, you will find usually people refer to this problem in terms of textual documents like this, where you have already a large portion or core, a text document, and you need to deep dive into that text document, try to recognize those tokens, and then classify them. However, in our case, it is different. Because in our case, we need to apply the same technique, the entity type recognition, but not for text or whole documents. This time, we need to apply it for queries. So if someone submits a query to my system, like the one at the top, that's saying senior Hadoop developer at Google. Then the new system or the entity type recognition system should understand senior is actually an entity and it refers to job level. Hadoop developer refers to job title. Google refers to a company. So if you look at this example now, you don't have much context to analyze in order to tell if this is actually a company, if this is actually a job title. How, from this very short text, can you tell that Google is a company or Hadoop developer is actually a job title? So the challenge when you apply that entity type recognition problem for queries is way more challenging than apply it on text or let's say documents. As I said, the challenges can be summarized as the search queries, as you can see, are short and contextless. Some entities have multiple surface forms. For example, University of North Carolina at Charlotte. The same entity can be referred to as UNCC or UNC Charlotte, right? So these multiple surface forms is another challenge. And the third challenge is the domain-specific entities. In our domain as recruitment or job board, if you take some terms like DON, if someone typed DON, Director of Nursing, how on the earth would you know that DON referred to an entity? Except if you are from that domain and you know that DON is Director of Nursing. So we have our own jargons, let's say, in the domain. And our systems suppose or have to deal with those jargons as well. So those are the challenges that make this problem more challenging in our case. So how people tend to tackle this problem? People rely heavily on Wikipedia. Wikipedia, Wikipedia, Wikipedia. Everywhere you go, you will find the solutions rely on analyzing Wikipedia, the knowledge in Wikipedia, different ways. So some people extract the title of the Wikipedia article and the first paragraph. And then they say, let's train a classifier using the title and the first paragraph, and then we can predict or know what the title of that page refers to or what entity type is. Other people used another features, which is, let's take the title of the Wikipedia article, and let's take the categories. In Wikipedia, each article has at the end categories section, right? So this is basically take that page title or article title, and then take the categories and train a classifier from using this data only to classify the title of that article. Is it a person, organization, location, whatever. Others relied on more structured kind of text within Wikipedia, which is the info box. The info box is kind of a semantic summarization of the article. So they try to take the info box and they train classifiers using info box to kind of classify entities, which they can extract from that article. Cool. Recently, with the new kind of available semantic knowledge bases like DBpedia and the Freebase, another kind of research track started to utilize those semantic knowledge bases like DBpedia and the Freebase. So why we can't definitely go ahead and apply any of those existing techniques? The first limitation is, how about if you have an entity that doesn't exist or doesn't have a page on Wikipedia? An example, Java developer. Maybe you'll be now kind of surprised. Oh, Java developer doesn't exist on Wikipedia. Yes, Java developer as a page or an article doesn't exist on Wikipedia. So if I rely on Wikipedia and I got an entity Java developer, which is very common query that we receive every day, I cannot tell that simple entity what it is. Non-standard categories. In our case, in our domain, skill, for example, when someone say Hadoop, I should say this is a skill. Spark, this is a skill. So skill is not a category anyway in Wikipedia as well. So if I'm planning to use Wikipedia technology or methodology that utilize the title and the categories. Skill anyway is not one of those categories. Domain-specific knowledge, as I said, DON, Director of Nursing, how would you find that on Wikipedia? Those jargons, you cannot find them in Wikipedia. So the answer is we cannot rely or leverage Wikipedia alone. So what is our methodology then? Our methodology is to combine or collect signals, features from different resources in an ensemble manner and train a classifier using those collected signals. We collect signals from Wikipedia, definitely, but we, on top of that, collect signals from the job postings within our website. We have millions, hundreds of millions of job postings stored in our databases. So what we did is, let's utilize, since we are talking about jargons and all those specific keywords used in our domain, if we rely on the millions, hundreds of millions of job postings that we have already, we should be able to catch or capture most, if not all, of those jargons. Then we also utilize the ontologies. So we use DBpedia, and we used on top of that also a lexical database, which is WordNet. Now let's move to the system design. So we have two, I would say, modes of our system. We have the offline mode and we have the online mode. And I'm going to describe why we built the online mode. So the offline mode, which was our first iteration or first version of the system, basically what we did is go to Wikipedia with an entity. But this time we don't go to the Wikipedia dump as a text. We actually take Wikipedia, we index it on a local Solr server in one of our data centers. So we have now Wikipedia indexed in Apache Solr, which makes the query in real time fast. Now the schema that we used to index the Wikipedia was also customized for our need. Then important part is what do we extract or which features we use from the Wikipedia documents. We use the title of the document, we use the length, we use the text, those are the fields that we index, and the categories. On the other hand, how do we utilize the knowledge in our job postings? Here, Spark comes. So we have hundreds of millions of job postings, as I said. And Word2Vec is the state of the art in NLP to find synonyms for each term or for each keyword. If we try to train Word2Vec on a standalone machine, it will take forever given the size of the documents that we have. So what we did is we utilized the Spark MLlib Word2Vec to train Word2Vec model using hundreds of millions of job postings that we have in order to learn the best representation of each word appear in those job postings. And then we use that Word2Vec model to generate synonyms. And synonyms are, if you say Java, C++, C# are synonyms to Java, for example, in our case. To generate the synonyms, or we call them the most similar or related keywords from the job postings for each term. And then we feed those features that come from Wikipedia and the synonyms that we got from Word2Vec, we feed them to an SVM classifier in order to recognize or to predict the type of the term. Is this a skill? Is this a job title? We have 5 classes: skill, job title, company, school, and location. Those are the classes that we use. Cool, so we built this and we run it, we put it in production. But then we figure out that, okay, now we can, for example, we had a dictionary but with limited number of predefined terms that we care about, the popular queries. But how about the terms or the queries that doesn't exist in our most popular queries list? if someone comes to our system and submit a query for something we never seen before. How can we handle that? And that's why we implemented the online system. So the online system that runs in the real time, let me just give you a little bit about the offline one. So the offline one runs actually in 400 milliseconds. So if I send an entity to this system, it takes 400 milliseconds to come back with the predicted entity type. I'm going to go over this architecture in a few minutes, but let me just go back and describe the online mode, and then we'll come back to describe those pieces of this of the system. But I wanted just to let you know about the time, because it's very important. So the time for the offline one is 400 milliseconds. Hit the classifier, generate those contextual features, return with the entity type. It takes 400 milliseconds. OK. So in the online mode, what we do is we take now, again, we indexed Wikipedia on Solr. So query or retrieving the Wikipedia features is not a problem because it is Apache Solr, which means you get everything in real time in terms of milliseconds. And then the word-to-vec, here's the trick. So the bottleneck when we ran the 400 millisecond things, we did kind of a test to find out where's the bottleneck. And the bottleneck was the word-to-vec. Because if you send an entity to the word-to-vec, asking word-to-vec to return to you the top 20 synonyms of that entity, that basically takes by itself more than 250 milliseconds. So that was the bottleneck. And we had to optimize it. And to optimize it, the best way in order to let this utilize the power of Apache Solr, which you can query in real time, and to get the advantage of the MLlib in Apache Spark, the idea was let's cache all the synonyms for all the entities that we extracted from our job postings in Apache Spark. So basically, we run the MLlib word-to-vec, we train a model, and then when you finish the training, the word-to-vec model gives you all the terms or the entities that has vector representation. You go over all those entities with vector representations, and you ask for each entity, you ask to get the synonyms list offline. You get the synonyms list, then you send them to Apache Solr. And then we have also two binary features, which one of them is company, another one has agent noun using the WordNet, and those are actually lookup, so they are pretty fast. OK. Back to the system. This is the offline architecture. As I said, we receive a query, and then we pass it to the Solr query parser. Then from Solr query parser, we send the query to a phrase identifier, which does the recognition of the pieces of the query that represent entities. And it is another work which I can chat offline about it. We call it a probabilistic query parser, if you would like later to go over the details. But it basically, if I have senior Java developer, Hadoop, how can I know that senior Java developer by itself is an entity, is a phrase? Hadoop is another thing now. So we do probabilistic query parser, which actually does that for us. And then once we recognize the entities, we send them down to the entity type recognition system. So we send the entity, and as I said, we send it to the Spark word-to-vec model. It returns synonyms. We send the same entity to Wikipedia index and to the DBpedia and WordNet to extract the binary features. And then we combine all those features in one vector representation, send it to the SVM classifier. Cool. How about the online? Because I don't want to run out of time, but how about the online? The online, I want you to look at the time now. For the entity type recognition in real time or in the online mode, Now we can get back the entity type of a token or of an entity in 30 milliseconds, 30. So this is very suitable for real-time query processing. So now this API, if you send to it an entity, in 30 milliseconds, it returns back to you with the entity type. As I said, the trick here, if you want to look at the difference between the two architectures or the two systems, the trick here is Apache Spark doesn't exist here in the online one. Why? Because the output of Apache Spark has been cached in Apache Solr. So we have now only to hit Apache Solr instances instead of hitting Apache Solr instance for Wikipedia and going to Apache Spark to get the synonyms. This is an example of the context features that we extract from Wikipedia. And this is just to show you how it's really meaningful, like the context features that you get from Wikipedia. On the other hand, on the other instances, it is not. So for IBM, for example, if you look to IBM here, you will find that the contextual features will let you know that IBM is related to multinational consulting corporation. Those kind of terms or keywords in the snippet can tell the classifier that this is a company. But how about the LPN, which is a job title, licensed practical nurse? Look to the stuff we got from Wikipedia. It's actually Lee person? Yeah. It's actually an article related to a person. So that's where it becomes misleading. And if you look to the syn sets, which is the synonyms we got from Word2Vec, from Spark MLlib, for LPN, when we train it on our job postings, we can, as you can see, we got the synonyms practitioner, LVN, nurse, registered nurse. So it tells exactly that this is actually related to a job title. So how did we evaluate our system? We actually did the evaluation using a data set of 177,000 entities manually labeled with their entity types. We trained the SVM classifier in the offline mode using this data set, and then we ran the different. We started with a baseline, which is bag of words. Just take the query as it is, don't add anything. And as you can see, schools, for example, did very well. Why? Because school has a pattern in their name, right? Schools have pattern. University of, right? Institute of. So the classifier, even with just the name of the school, was able to detect a pattern and perform very well. However, for a skill, 76%, we cannot go online or start serving in production with this quality. Then we applied the Wikipedia features, and the Wikipedia, we trained a Word2Vec using Wikipedia documents. This is the first experiment. Then we applied the Wikipedia context, which is the features I talked about that we extracted. And then we applied the Wikipedia context and the Word2Vec, which we trained on our job postings. And finally, we add on top of that the ontology features, which is the DBpedia features, and the WordNet feature, the binary features. And as you can see, the green numbers represent that we boost the accuracy by this number in all the classes. So to conclude, the ETR is very important actually for the search query understanding, for the query understanding. And what we implemented is ETR system that can work in offline mode and in the online mode by integrating Spark, MLlib, and Apache Solr to serve that goal. And we have a full research paper about this. It was published last year in IEEE CompSec. And here's a link on archive to that paper if you would like to get more details about the work. And thank you. Thanks for your time.
And I think we've got a few minutes for questions. Did anyone have any questions for Khalifeh? Yes.
First, thank you. This is great. I have a question about like this approach that you have used for actually related to jobs. Is it could be applicable, for example, for insurance companies? Like they have a lot of documents, and sometimes they want like.
Yeah. So the question is, the technique that we use for job postings is it applicable for other domains? And the answer is yes. Any jargon, any domain-specific corpus can be. You can train a word-to-vec using MLlib to use that corpus to learn the representation of the words from that domain-specific corpus, and it should be more accurate to predict then based on that vectors of those words than training it on a generic corpus like Wikipedia. That's our finding. So if you train on Wikipedia, it's a generic corpus. But if you train on specific, like in your case, the insurance documents or whatever, it should be way more accurate. So it is, yes, it is applicable.
Another question here.
Sure.
Yeah, so first, this is an awesome talk.
Thank you.
I have questions about, so how do you implement the phrase detection or like face identify?
That's a great question. Yeah. Okay, yeah, we still have a few minutes. So I'm gonna give now kind of, I'm gonna highlight the way, the methodology, but if you would like to chat offline about more details, I can provide more details. So we built a language model where you go on your corpus. In our case, it's job postings, okay? And you try to calculate the probability of seeing unigram, bigram, trigram, up to 4 gram, okay? And then, based on the probability, you calculate those and then you store them, you cache them. So you say that Java, the probability of seeing it as a unigram is, for example, 0.9. Java developer still is a valid phrase as bigram by 0.8, okay, and so on. Once you have those unigram, bigram, trigram, probably you care about the bigram, trigram, up to 4 gram. Unigram, you don't care much about it. So once you have that, then what you can do is you can, whenever you see your query, you start with the 4 gram, and you send it to your index, and you see, do I have a valid 4 gram like this? If yes, then it is a valid one. If not, then you go to the trigram. If not, then you go to the bigram, and so on. So that's the phrase identifier, basically.
We have another question back here.
Sure.
First, thank you for the awesome talk.
Thanks.
So I used to work on a very similar problem, and I especially like understanding the query, and it was in the job domain as well.
Cool.
But we took a very different approach. Instead of using things like word embedding, we use user behavior. So the idea is if a user he searches to queries in the same visit, so usually those queries are highly related to each other.
Right.
But in your approach, you user behavior didn't really fit in your framework, or you never actually tried that?
That's a great question, and I should say that maybe we can offline again chat about it, but we have built a model called Probabilistic Graphical Model for Massive Hierarchical Data that mainly was extracting the related search terms using the same thing which you described. Searches come from the same user in the same session. We represent them, and then we extract the vectors of each word from the related words or the related search terms which the users actually used in their sessions. And we have 2 papers published about that work. I can definitely chat with you offline about them. And I gave actually, there is a published presentation which I gave last year from keyword-based search to language-agnostic semantic search. That's on SlideShare, you can find it. That talk was mainly about this idea of using the behavioral data to predict or to infer the related search terms, semantically related search terms. But yeah, that's definitely a very good point because this is a very good technique that we already use.
All right. Any more questions, guys? If not, thank you very much, Khalifeh. We're going to take a 10-minute break. Yeah, let's give Khalifeh a hand, and we'll have our next speaker up in about 10 minutes, guys.